This is our fourth and last geometric optics video, and in this video I'm gonna look at some more little bit more complicated questions related to geometric optics. So let's look at some of them. In this question they say parallel beam of light enters a glass hemisphere perpendicular to the flat face as shown. The radius of the hemisphere is 6 centimeters and the index of refraction is 1.56. Determine the point at which the beam is focused. Also assume that the rays are paraxial, that is, assume that all rays are located close to the principal axis. So I will use the equation, the one that we have with the index of refraction. So I have N1 over d to the object plus N2 distance to the image and equals to N2 minus N1 and divided by the radius of curvature. Because the rays are coming from the glass into the air, so our N1 is 156 and the distance to the object is infinity, so that this part of the equation is going to turn into 0, plus N2, which is air, and it's going to be 1 over di, and that is equal to N2 minus N1, so that is negative 0.56, and divided by the radius of curvature, which is given to be 6 centimeters, but it is the divergent length because of this part, so it's divergent, so that is negative 6. So if I do my calculations for di, I will get 10.71 centimeters. In this next question, they say two converging lenses are placed 20 centimeters apart as shown, with an object placed 30 centimeters in front of lens 1 on the left. If the lens 1 has a focal length of 10 centimeters, locate the image formed by the lens and determine the magnification. If the lens 2 on the right has the focal length of 20 centimeters, locate the final image formed by the second lens and find the total magnification of the system. So for the first lens, we're going to follow the rules for the rays. We have parallel through the focal length, then through the focal length and parallel, and then one through the center without the refracting. So here is going to be the image for the first lens. And for calculations, we have 1 over the distance to the object, which is 30 centimeters, plus 1 over the distance to the image we are calculating, and equals to 1 over, and the focal length for the first lens is 10. If I times them all by 30, I get 1 plus 30 over di, and equals to 3. So di is equal to 30 over 2, which is 15 centimeters. And now this becomes the distance of the object for the second lens. So for the second lens, we have parallel to the axis and then through the focal length, and the focal length is 20. I don't have it here to fit, so it would go far away. And through the focal length, and the focal length is right here for the first one, so that would be through the focal length, and then it would be parallel and through the center. And if we prolong the rays from the ones that are coming, like here is the one and here is the next one. So you see the image for the second lens is gonna be virtual, and it's gonna be on the same side where the object is, and the object is in red. So let's calculate this. We should get the distance to the image negative. So for the second lens, we have 1 over the distance to the object. So the distance to the object is going to be, so the distance here is 20 centimeters between two lenses, and this distance is 15. So this one is 5 plus 1 over the distance to the image we're looking for, and equals to 1 over the focal length, which is 20. The common denominator is 20, so I'm going to times them all by 20 and I have 4 plus 20 over di, and equals to 1. So di is equal to negative 20 divided by 3, which gives me negative 667 centimeters. So this is where the image is going to be located. So this distance should be 667 centimeters. And to calculate magnification, for the first one, if I do magnification, it's negative di over do, so that is 15 over 30, and gives me 0.5 negative. And for the second one, I have the magnification, negative di, the same formula. So that is 667 to the distance of the object, which is 5, and that will give me positive 1.33. And the total magnification for the problem is m1 times m2. So that is negative 0.5 times 133. And that will be negative 0.665. In this question, they say the object in figure is midway between the lens and the mirror. The mirror's radius of curvature is 20 centimeters. I'm going to underline it so it's going to be easier to find later. And the lens has a focal length of negative 16.7 centimeters. Considering only the light that leaves the object and travels first towards the mirror, locate the final image formed by the system. Is the image real or virtual, and is it upright or inverted? And what is the overall magnification of the image? So we will start with the mirror, and for the mirror we have 1 over do plus 1 over di equals to 1 over the focal length, and the object is placed midway between the mirror and the lens. That is, the object is placed 12.5 centimeters away from the mirror, so the distance to the object is 1 over 12.5 plus the distance to the image we are calculating, and the focal length of the radius of curvature is given 20 centimeters, so the focal length is 10. So if I do these calculations, I will find that di for the reflection from the mirror is going to be equal to 50 centimeters. That means it's going to be located on the left side of the lens, 25 centimeters away. So that means that the image of the object is going to appear 25 centimeters past the lens. So this distance is 50 centimeters. So the image is going to appear somewhere right here. And the magnification of the image is equal to negative di, which is negative 50, to the distance to the object, and the distance of the object is 12.5. So the magnification is equal to negative 4. So that means the image is inverted and the image is real. And so the image is going to be, again, somewhere over here and looking down. And for the second part, so this was for the mirror. Now for the lens. For the lens, we have this image as an object. And this object is virtual. So when I plug into my equation, the distance for the object is going to stay negative. So I have negative 1 over, and the distance here is 25 centimeters, and this is also 25 centimeters, so together gives you 50 centimeters. So I have 1 over negative 25 plus 1 over di, and equals to 1 over the focal length, which is negative 16.7. Then my di for the lens is going to be negative 50.3 centimeters. And for magnification of the second one, I have negative di over do, and negative will give me positive 50.3, but the distance here is negative 25. So I get negative 2,012, the magnification for the second time to get image for the lens. And the total magnification of the object is going to be the product of both of them. So this is the 1 and 2. So it's negative 4 times negative 202. So I'm not going to write this part. I'm just going to write the answer. So that is going to be 804. And the image is going to be virtual because the distance is to the image is negative, and it is also upright because it has been flipped or inverted twice. We got the magnification is negative, so that means the image has been inverted second time, and also this one is upright. It tells you that it is upright at the end, or in the same direction as the object. A meter stick lies along the optical axis of a convex mirror of focal length of 40 centimeters. So it's a convex mirror with a focal length of 40 centimeters, with its near end at 60 centimeters from the mirror. So this is 60 centimeters, and it's a meter stick, so the other end is at 160 centimeters because 1 meter is 100 centimeters. So 5 centimeter toy, so the toys are 5 centimeters, so each of an object is 5 centimeters. Figures stand erect on both ends of the meter stick. How long is the virtual image of the meter stick, and how tall are the toy figures in the image, and are they erect or inverted? So at first I'm going to find the distance to the first image. Using the lens law, I have, maybe I'm going to write it on the side, 1 over do plus 1 over di is equal to 1 over f. So I have 1 over 60 plus 1 over di and equals to 1 over the focal length, which is 40, but it is convex mirror, so the focal length is negative, so I have negative 40. So from here I'm going to find that di is equal to negative 24 centimeters, If I try to draw the lines for the convex mirror, I have parallel through the focal length, but the ray cannot go through the focal length, so it's going to be reflected in this direction. And then I have to the focal length, so it's going to go toward the focal length, and again it cannot pass through the focal length, and then reflected parallel to the axis. And the last one would be to the center and incident angle and reflected angle, but I already can say where the image is located. So if I prolong this line this way and that line that way, so the image is going to be right here. So this is where the distance is -24 centimeters. And if I do the magnification, I have, so the magnification formula is -di over do. So I have, and hi over ho. So -di, so that's 24, and the distance to the object is 60. So that will give me 0.4. So it's less than half of the toy itself. And then the same I'm gonna do for the second toy. And I will have 1 over 160 plus 1 over di, and equals to 1 over -40. So in this case, I will get di equals to -32 centimeters. So for the second image, I'm gonna have the distance -32. So the focal length is 40, so that means the second one is gonna be somewhere here. And they ask you how long is the vertical image of the stick, virtual image of the stick. So the stick itself is this long, and that's the difference between these two guys, and that is 8 centimeters. So the meter stick, so the stick is going to be only 8 centimeters long, the virtual stick. So this is the answer for this question. And then let's do magnification of the second image. So that is -32, with a negative gives you +32. So -di over do, which is 160, and that is equal to 0.2. And they ask you how tall the figures or the toys will be. So for the first one, to calculate the height, I'm going to use this formula, hi over ho. So I have 0.4 is equal to hi, the image size, over ho, and the height is 5 centimeters. So that will give me 2 centimeters. So hi is 2 centimeters for the first. And for the second one, maybe I'll do it in different color. For the second one, the magnification is 0.2, and I'm looking for the second height. It's 5 centimeter toy. So that will give me hi is equal to 1 centimeter. So that answers this question. Suppose you want to project the image of a transparency, the height of which is 35 millimeters. So the image is 35 millimeters. So this image right here is going to be 35 millimeters. On a screen that is 1.5 meters high. So this screen right here is 1.5 meters high. And to a screen that is 1.5 meters high, using the lens with a focal length of 10 centimeters. So the focal length of 10 centimeters. So because I have millimeters, meters, and centimeters, I have to convert this problem all in meters. And the questions they have are, where would you position the film and how far from the lens would you place the screen? Because we have the inverted image and it is real, we are talking about the converging on convex lenses. So the first part I can do is to find the magnification. The magnification is equal to HI over HO. And HI is 1.5 and HO is 0.035. I have to convert into meters, and that will give me negative because I know that it is inverted, so the image is going to be negative. So I have negative, and the number is 42.8. So the image is going to be inverted compared to the object, and it is 42.8 times bigger. I'm going to draw these two rays. So one is from the bottom of the tree, and the other one is from the top of the tree. I see that I have two triangles right here, and their angles are the same here, and their angles the same along the base side, because those two base sides are parallel. So I have two similar triangles, and because this side is let me do it in red, because this side is 42.8 times bigger than this side of the triangle, then that means that the distance to the object and the distance to the image have relationships. The distance to the image is also 42.8 times the distance to the object. Now, if I use my lens equation, 1 over dO plus 1 over di is equal to 1 over f. So dO is going to stay as dO, and for di I have 42.8 dO, and the focal length is I'm gonna keep in centimeters, so my answer is in centimeters, so that's 10, because none of the other measurements have to be in meters or centimeters. So from here I can find that dO is equal to, and I did some simplification for you so you see what it is. So I get 10.23 centimeters. So that's the answer. Where would you position the film? And how far from the lens would you place the screen? And the screen distance, di, is 42.8 times dO. So this is 42.8 times dO from over here. So di would be equal to 438 centimeters, because we chose to be everything in centimeters in our equation. So my answer is in centimeters as well. And the next and the last question, they ask you where must the film be placed if camera lens is to make a sharp image of any object very far away. And in this case, the film should be placed at the focal length of the camera lens. Then you get the object to be in the infinity. We covered this in our first video when we Geometric Optics 1, when I explained the images of different type of positions for the object. So every time the object is at the focal length, you get the image in the infinity. This will conclude our last video on Geometric Optics, video number 4. And if you have questions, then go ahead and email me and ask me questions about the problems you find in our lessons that you had trouble with. And I will be very happy to email you the answer or post the answer in form of the video. And thank you for watching this video, and I will see you in the next one. The next series of videos are going to be on modern physics.